All right. Did you get that? Whew. That's some tough stuff. What I'd like to do is maybe work through a couple examples with you, and I think by the end you're going to get it. It all comes back to the right-hand rule and boiling Lenz's law into a simple series of steps. If you can handle that, you can figure out the direction of the induced current caused by Faraday's law. All right? Now let's try it. So, on that piece of paper where you were taking notes, here's what I would like you to do. Can you write out our first example? Let me get that in a good spot for you. There it is. All right. So what we're looking at, go ahead and write and draw while I'm talking. What we're looking at is a magnetic field that is staying constant, and it is pointing into the plane of the paper. That's why we see the X's. We have a loop that starts off outside of the field. Therefore, the flux is going to be 0. And then some external force is going to pull that loop into the magnetic field. When it does that, there's going to be a change in the flux. And that is going to induce a current within that conducting wire, within that loop. So the question is, which way is the current going to go? Clockwise or counterclockwise? Slow down. First of all, you get out your trusty physics coin. The answer is counterclockwise. Hey, you got a 50% chance. Or you use your noggin. Let's do this. Here's my loop. Okay. It is going into a magnetic field. When it does that, it's going to produce its own field that opposes the change in flux. So my first question is, what happens to the change in flux? Is it increasing or decreasing? The answer is that the flux is increasing. It started at 0, and then there is a magnetic field in the loop, so the flux is increasing. Therefore, the B field that's induced in the loop is going to be opposite in direction. It's going to be opposite the change in the flux. And since the flux increased, the B field produced is going to be in the opposite direction. Now, if the B field is in the opposite direction, that means it's going to produce a B field that is pointing out of the paper. Yeah. And if the B field is pointing out of the paper inside that square, which way does the current have to be going? Clockwise or counterclockwise? Well, I get my left hand out. That's my right hand. I get my right hand out. I take my fingers and I put them in the direction of the induced magnetic field, which, if I pick the right-hand side of the wire, I put my palm against the wire, the field coming out into my eyeballs, and my thumb is pointing up. Now, I know you're thinking, what if I chose a different side? Let's choose the top of this, okay? Put the wire against your palm. Fingers coming out at you, wires against the palm inside the square. My thumb, whoop, whoop, is pointing this way. I know that Zoom reverses me. Next, I put my palm against the other side. My thumb points down and it goes around. Check it. Right now, get your right hand out. Put your hand inside the loop. So it's going to be inside at each point with the field it makes coming out towards your eyeball, onto the plane of the paper, and your thumb gives the direction of the current. Therefore, The current is that the direction of a clock? No, it's not. So we call it counterclockwise. And in the end, that is your final answer. And that's not a Mr. Edgar abbreviation. That's standard. CCW, counterclockwise. Whew. Let's try the next one. Yeah. Of course you don't get it yet. Relax. Oh, some of you do. The rest of you, relax. Let's get the next one. Open up your mind. Here we go. Example number 2. There is a B field pointing out of the plane of the paper. So all you see is the dot. There's a loop of wire that starts off in that B field that is then pulled out by some external force. Therefore, the flux is going to be decreasing. If the flux decreases, Lenz's law said the B field induced will oppose the change in flux, or basically be in the opposite direction of the change in the flux. So if the flux is decreasing, the B field induced is in the same direction. It's opposing the change in the flux. Therefore, if the B field is in the same direction, what direction does the current have to be in order to create that B field? Well, you put your hand in the loop and it's going to go one way or the other, right? If I put my hand in the loop with the fingers coming out, again, I'm reversed. Take your imaginary loop or look into the screen. Put your hand so that they're coming out towards you. My thumb, whoop, 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 is going to be going, again, counterclockwise. Yeah, I felt a few more of you get it that time. It's that the direction of the B field is in opposition to the change in the flux. Okay, next one. Oh, baby. Kind of gave a little bit away here. Let's try this. Go ahead and draw in a bar magnet. Now that bar magnet is going into a loop of wire. This is almost identical to my first lesson on Faraday's law when we use the galvanometer. So I'm taking the magnet, and this arrow right here indicates that it's getting closer. So the B field, the B field is actually going to be pointing out of the north. Let's go ahead and draw that in. B field comes out of the north. Yeah? Now, it says in this problem that the magnet's getting closer. If the magnet gets closer to the loop, then the B field increases. If the B field is increasing due to the motion getting closer and closer to it, the flux is also going to be increasing. If the flux is increasing, then the induced B field is opposite the change in flux. Therefore, it's going to be in the opposite opposite direction. I can do Lenz's law, but I can't spell opposite. Now, what does that mean? It means that the B field produced by the current is actually going to go in that direction. So the B field produced by the loop is going this way. So what does that mean? It means Get your right hand out. Put it so that your fingers are going through the loop. Through the loop, and your palm is against the loop, like this. And you do that, and your thumb gives the direction of the induced current. Oh, yeah, you guys, I just felt it. I felt a few more of you get it. Now this actually is the direction of a clock. So it's clockwise. Now those of you that were brought up using digital clocks, good luck. If you got one of those fancy Apple Watches, you can change it from digital to the clock dial. Maybe you'll figure it out that way. Clockwise. Okay.